We are first 5125 Hawks in the Horizon, and we are excited to share the making of Jabba Da Noodles, our infinite recharge robot. We are very fortunate to have competed in the Midwest Regional, where we placed 8th Alliance Captain, and we're 12th out of 54. Our robot was built to be efficient and practical, yet aesthetically pleasing with our team's black and orange scheme. Our machine was designed around specific requirements which we developed through our engineering process. The first step we took is to thoroughly learn the game. The entire team watched the game animation and wrote down questions about the game. We repeated this until we had no more questions to ask. Then we split into groups, divided the questions, and dove deep into the game manual to answer them, ensuring all members have a thorough understanding of the game rules. As a team, we reviewed answers and noted if there are any clarifications were needed.
We then list out all of the actions a robot can do, such as pick up power cells and even just moving. We created a decision matrix and rated each action on 4 different criteria: scoring, build complexity, helpfulness, and difficulty to control. As you can see, our top priorities for this year were to move, manipulate the control panel, and shoot for the lower port.
Based on our discussions, these actions led to our 2020 season strategy. So score in the lower ports, pass power cells to teams, and spin the control panel. As a team, we've reached a consensus on every rating for every criteria for every action. While this process lasts a while, it allows us for deep discussion about the strategy.
For our design process, our team split into groups and began designing and prototyping the robot mechanisms to fit our strategy. After a week of this process, each group presents and we finalize the design as a team.
The mechanisms and control systems subteam directors meet after our design phase to develop a Gantt chart with a list of tasks and a timeline for the completion of our robot. Technical directors meet weekly for the duration of build season to update progress on the Gantt chart and to coordinate meetings.
Our drivetrain is a 6-wheel tank drive built from the kit of parts. Our drivetrain runs at a maximum of 12 feet per second and uses 2 stem motors to drive each side. Over the years, we've recognized our tank drive is robust, cheap, swift, and defensive on the field. We've placed significant thought into our bumpers. We catted the wooden frame to ensure it matched the drivetrain precisely. Wing nuts that hold the bumpers in place allow for quick removal. Our one-piece wraparound bumpers were designed to be aesthetically pleasing as well.
The power cell system is made up of 3 mechanisms that were built to work as one: the intake, the conveyor belt, and the shooter. We wanted the system to hold 5 power cells, capture power cells as soon as they were touched, and shoot reliably into the lower port. Per our robot design process, we came up with 3 distinct ideas, which were prototyped using wood, cardboard, duct tape, and CAD. Our first idea was a C-shaped conveyor belt seen here on the left, which wasn't effective because the power cells got caught in the corners. Our second idea was to have belts on the side of the robot, but did not hold 5 power cells. Our last idea was to have belts on the top and bottom, which allowed for 5 power cells to be held side by side. We chose the third idea because it fit our design requirements.
With our design confirmed, we used CAD to determine precise measurements and ensure all 3 mechanisms were integrated seamlessly. This process was vital as it established the primary structure for our robot, ensuring high quality during fabrication with attention to aesthetics.
Our intake system, powered by an RS-775 motor, has 7 4-inch orange compliant wheels, pulling power cells into the running conveyor belts. The black bar above the mechanism holds the frame together and prevents damage. After assembly, we realized power cells were getting through a 1-inch space between the intake wheel and conveyor belt, so we added a metal rod to ensure power cells stayed on the right path. The conveyor belt in the middle of the robot is operated by the 12 polyurethane belts, which provided a better grip to power cells and easier to fabricate. They are run by aluminum rollers with rope underneath each belt, holding them in place. We built a reverse pulley that allows a single RS-775 motor with an 81-to-1 gear ratio to power both the top and bottom belts. Custom gussets were used to extend the bottom belt to the ground. 13 4-inch orange stealth wheels powered by a 4-to-1 gear ratio and an RS-775 motor shoot power cells. A piece of polycarbonate above the shooter creates pressure to allow power cells to release with more force.
We thought of various ideas for the control panel mechanisms, whether to use a piston versus a motor, 1 motor versus 2, and the wheels on the side versus on the top. After discussing the pros and cons, we've decided to use a piston, 1 motor, and putting the wheels on the side. A prototype was built as seen on the right and later refined in CAD on the left.
When not part of our initial strategy, we found ourselves with extra time and looked for a quick hanger solution. Fortunately, we found a great hanger design from Team 118, the Robonauts. We fabricated custom gussets to attach to the hanger to a 2x1 bar across the drivetrain, ensuring that the robot was lifted at multiple points. The hanger moves up and down due to the tension between the springs and the motor, which is an RS-775 with a 49:1 ratio. A ratchet wrench with 2 bolts on each side prevents the hanger from being back-driven.
For control systems, we created a wooden prototype to lay out electronics, check wiring routes, and determine accurate measurements. This allowed us to begin programming while finalizing space constraints. Limited space led us to create 2 levels with motor controllers on top to be easily visible for troubleshooting. Aesthetics and wire management played a large role in our design. We used the frame to our advantage to route wires to be hidden and secure. We used 2 Talon SRXs and 7 Victor SPXs to control our motors. Talons are used for the shooter and conveyor belt due to better performance and reliability. We also use a gyroscope to help steer the robot during autonomous and a Logitech USB camera to help view the intake system from afar. For autonomous, our robot was designed to go backwards for 3.5 seconds and shoot all 3 preloaded power cells. This slide shows our code and a GIF of our autonomous one.
We'd like to thank you for your time and we'd be happy to answer any of your questions.